My name is Pascal Poupart, and in this module I will give an overview of imitation learning, which is an important topic for reinforcement learning. Imitation learning refers to this idea that we want to train an agent to imitate a domain expert. Now, there are several ways in which we can do this, and we're going to start with the simplest, which is known as behavioral cloning. Here, behavioral cloning is an approach where we train an agent in a supervised manner to imitate an expert, where we observe the actions of the expert. Another approach is to use generative adversarial imitation learning, and as you probably have guessed, it is related to generative adversarial networks. So the idea is that we're going to generate some actions that imitate those of an expert, but we're going to also use a discriminator to essentially tell whenever some actions are real versus generated in order to help our generator get better and better at producing actions that imitate those of the expert. The third technique is known as imitation learning from observations, and here this refers to this idea that we're not going to observe the actions of an expert, but only some consequences of those actions. And we're going to call those consequences observations. So the idea is that we observe the outcome of those actions, like observations or states, and then we're going to infer back what are some of the actions, and then train a policy to imitate what are those inferred actions. Finally, there is a very important technique, also known as inverse reinforcement learning. Now, we're not going to cover it in this module, but it is very important, so we're going to dedicate an entire module to this technique, so this will be the subject of the next module. Imitation learning is an important paradigm for several reasons. So first, we do not need a reward function. So if we consider traditional reinforcement learning, there's a reward function that defines the objective, and the idea is that we then train a policy to optimize that reward function. But in many domains, we're not sure how to design the reward function, and it's really not clear what are the objectives. So the idea is that if we have instead an expert who can demonstrate a good policy, then even though it's not clear what it is that this expert is really optimizing under the hood, then we can directly bypass the reward function and imitate what that expert does. Another aspect is that the learning can be sped up considerably by imitation learning. So here, normally in reinforcement learning, we would have to do a certain amount of exploration at the beginning, which might be costly in part because we're going to execute actions that are not very effective, and it does take some time before we arrive at a good policy. But if we have an expert that can demonstrate a good policy, then we don't interact with the environment yet. We simply observe what the expert does, and then we can learn directly from those demonstrations, and very often we can obtain a very decent policy this way. Now, there's several domains in which imitation learning is attractive. So first, if we consider humanoid robots, then if we'd like those robots to perform some tasks that are similar to what humans already do, then we can get a person to demonstrate the task a few times, record the data, and then train the robot to imitate what that person just did. Another important domain are chatbots. In particular, if we consider the problem of customer assistance, then often there would be already some customer agent who would know how to answer various questions from the customers, and if we record their answers, that provides us with some demonstrations on how to answer the various questions. A third domain that is very important is autonomous driving. So in this case, we as humans are already pretty good at driving, so we can provide lots of demonstrations. And it turns out that learning by imitation for autonomous driving can be quite effective. It's in fact one of the simplest ways to obtain a decent policy just by training one system end to end by imitating the type of actions that humans are taking. Behavioral cloning is one of the simplest forms of imitation learning. So we're going to start with this technique, and then we're going to make an important assumption, which is that the sequence of state action pairs from an expert can be observed at all times. So here we're going to formulate behavioral cloning as follows. So we observe trajectories from the expert demonstrating a policy, ideally an optimal policy. And here, for us, it's really the sequence of state action pairs that matters. Then we're going to create a training set where for every state, we're going to have the corresponding action. And the idea is that we're going to do supervised learning to train either a classifier or a regressor to predict what is going to be the action of the expert in each state. So here we'll use classification whenever the actions are discrete, and we're going to use regression whenever the actions are continuous. An important application of behavioral cloning is autonomous driving. In fact, if we go back to the 1990s, one of the first approach for training a system to drive autonomously was via behavioral cloning. And still today, this remains an important approach. So what I've got on this slide is the schematic of a system that was designed in 2016 by Bojarski et al. For end-to-end learning for self-driving cars. So the top part of this design is where we record the actions performed by a human driver. So the human is holding the wheel, essentially performing some steering commands, and these get recorded as a sequence of actions. Now in parallel, we also have a left camera, center camera, and right camera, essentially recording some snapshots of the world. So that gives us an estimate of the state. And now this state, in conjunction with the steering command, which is the action, now gives us a tuple that we can use to do some supervised learning. So in their design here, they use a convolutional neural network to predict what are the steering commands of the human driver in each state based on the information recorded by the left, center, and right cameras. So whenever the prediction of the steering command is not accurate, then an error is measured. We can use backpropagation and essentially train this convolutional neural network to improve its predictions. So Bojarski et al. Did this work by training in a supervised fashion in simulation, but then they also did some tests on the road. And so in the first experiment, they went from Holmdel to Atlantic Highlands. This is in New Jersey. And then the car was able to drive 98% of the time autonomously. In a second experiment, they took the car on a highway, and this was the Garden State Parkway, where it drove for 10 miles without any human intervention. So this is remarkable because it's a simple approach where we simply observe what a human does by driving these same segments, and then the car can imitate and drive decently. Obviously, unless it is very robust, this would not be sufficient, but it is a good starting point to obtain a basic autonomous driving system. A second application of behavioral cloning are conversational agents. So here we're looking at a question, how are you doing? And in conversational agents, the first step would typically be to use some form of recurrent neural network to encode this question into a state. Then after this, we have a decoder that will produce the action, which corresponds as well to a sequence of words. For instance, the system could respond with "I am fine," and again, this is the action that is produced. Now, to train a system in this fashion, we can use supervised learning again. The idea is that we're simply training to maximize the probability of actions given states. In other words, if we have a data set of message response pairs that have already been recorded based on some conversations between some humans, then we can treat the messages as states, the responses as actions, and then we can train this type of encoder-decoder model to mimic or imitate the type of responses that a human would produce. Now, what's a little special is that the states and the actions are really multidimensional. So here, the state would correspond to an entire sequence of words, and similarly, the action is also a sequence of words. So in terms of predicting an action, then what we're really doing here is predicting a sequence of words, and we can express this simply by decomposing our probability of A given S by a product of the probability of each word given the previous words in the response, as well as the state that corresponds to the original message. In 2015, Sordani et al. Wrote a paper where they showed some examples of the type of message response pairs that can be achieved by this type of supervised learning. So on the left side, we've got the context, which is what happened earlier in the conversation. Then in the middle, we have the message, which is essentially the state that was written. So these are messages that are written by a human. And then on the right side, we've got the response, which is the action that is generated by the system. And then if you look at those examples, the responses do make sense in the context of those messages and are quite reasonable. Imitation learning can be achieved in several ways. So far we've looked at the simplest approach, which is supervised learning. And in particular, we can do supervised learning by maximizing the likelihood of the expert actions. But then an alternative could also be to use generative adversarial networks and to train a generator to fool a discriminator in believing that the generated actions are really from an expert. So this is another technique that has become quite popular in recent years, and now we're going to see how it can be applied specifically for behavioral cloning. Before going into the details of generative adversarial and imitation learning, let's have a quick recap of what are generative adversarial networks. So generative adversarial networks consist of two components. The first one is known as the generator. The generator will take as input a random vector z and then output some data. Because this data is not real and it is generated, we're going to denote it by x tilde. So for example, if we'd like to generate images that correspond to faces of people, then we can train a generator to turn some random vectors into images, and ideally images that contain faces or faces that are as real as possible. Then the second component is a discriminator. It takes as input data points and it needs to determine whether those data points are real or fake. Whenever the data was generated by the generator, then it is fake data, so the goal for the discriminator is to identify it as fake. Now we're also going to feed some real data to the discriminator, and then its job will be to identify it as real. We can train simultaneously the generator and the discriminator by min-max optimization. So here this is a little different than traditional maximum likelihood because we have this dual objective for training both the generator and the discriminator simultaneously, and we're going to do this again by min-max optimization. Here I'm going to denote the parameters of the generator by theta and the parameters of the discriminator by w. This objective, we're going to maximize it whenever we're adjusting the parameters of the discriminator, because this objective corresponds to essentially the probability that the discriminator correctly distinguishes data that is generated as fake, so this is our second term in the objective, versus data that is real as real. Now in contrast, the generator, its job is going to be to fool the discriminator, so we'll try to minimize these probabilities. We can rewrite this objective where here instead of talking about the probability, I'm just going to use d to indicate that is the discriminator. So we can see that the first term now is just d applied to x, and that should return a probability that x is real. The second term is 1 minus d of g of z. So we've got the generator applied to the random vector z, and then that is fed to the discriminator. And here we would like to identify this as fake from the perspective of the discriminator, and so that's why we take 1 minus the probability that the discriminator produces a probability that it's real. So this is the objective that is typically used in GANS, and now we're going to see how to adapt it for the perspective of imitation learning. We're now ready to define some pseudocode for the generative adversarial imitation learning algorithm. The input to the algorithm will consist of some expert trajectories, and we're going to denote them by tau e. Here, tau E corresponds to some state action pairs that are executed by the expert as demonstrations to the agent who's learning. Then our first step will be to initialize the parameters theta of the policy pi and the parameters w of the discriminator d. We can do the initialization in all kinds of ways, but what is common is just to initialize them at random. Then we're going to enter a loop that will alternate between two steps. First, we're going to update the discriminator, then we're going to update the policy. So let's have a look first at the update of the discriminator. So if we go back to the previous slide, we saw an objective for generative adversarial networks, and then we're simply going to take the gradient of that objective to obtain a direction that we denote here by delta W. So here you see the first term for this direction is the gradient of the log of D applied to SNA, where SNA correspond to state action pairs that are obtained from the expert trajectories, and in that sense it's real data. So that's why we would like the discriminator to simply maximize the probability that it detects this as real data. The second term is looking at the gradient of the log of 1 minus d applied to SNA, but this time SNA is data that is generated by our policy pi, so in that sense it's fake data. So in the second term, that's why we take 1 minus d, because we'd like to effectively reduce the probability that the discriminator detects this as real, since it's really fake. So together, those two terms give us the direction delta, and then we take a step with a step length alpha to update W. The next phase is then to update the policy parameters, and we're going to do this with the TRPO algorithm. So here this is the trust region policy optimization algorithm. Now, when we look at the objective that we've been optimizing, it's only in the second term that the policy pi appears. So we're going to define a cost function that depends on this second term. So here you see we take the log of 1 minus d of S and A, and that's because S and A depend on the policy pi, and we're going to look at all the state action pairs that are arrived at when we execute our policy pi, starting from some initial state and action pair S0 and A0. So this defines a cost function because here the generator is trying to fool the discriminator. So in other words, we're going to try to minimize this term. Now we're going to use this term to define the direction in which we're going to update the parameters. And then for that, we have a first term where we take the gradient of the log of our policy pi times our cost function. And then we subtract from that a second term where we have the gradient of the entropy. So the idea is that the first term corresponds to a gradient update according to TRPO, and then the second term corresponds to maximizing the entropy of the resulting policy. So together that gives us a direction delta, and then we take a step with a length alpha in that direction to update theta. Let's have a look at some experiments in the context of robotics to compare generative adversarial imitation learning with behavioral cloning and a few other baselines. So on this slide, we have 8 robotics domain, and then the y-axis indicates the performance, which has been rescaled between 0 and 1. Here 0 corresponds to a random policy, and 1 corresponds to the expert policy. So the idea is that we want to achieve a score that is close to 1, indicating that we're imitating the expert policy. We can see GAIL, which is in blue and corresponding to a solid line. So the GAIL algorithm, generative adversarial imitation learning, tends to approach a score of 1, which means that it is doing a pretty good job at imitating the expert. In contrast, behavioral cloning, which is in orange, does require more data and is not as stable. So generally speaking here, doing supervised learning doesn't perform as well as GAIL, which is doing this min-max optimization, by using a generative adversarial network. So far, we've seen that imitation learning can be quite effective in terms of generating a good policy that imitates an expert. And in several applications, the expert will be a human. However, when we have an expert that is a human, the type of actions that the expert is executing might not be directly observable. So for instance, if you consider here the task of getting a humanoid robot to imitate a human, we can put some sensors or otherwise some form of tracking to essentially track the position of the joint of the human, but that does not give us what are the actions that the robot should execute. So for the robot's perspective, the action would be different forces, and that's different than the positions of the joint. So here we have the following problem where sometimes the actions of the expert are not observable. Instead, what we can observe are going to be states or observations, and for this examples, it would be perhaps the position of the joints. So the problem that we are facing is that in imitation learning, we might have to do imitation learning from observations only, where the states are not directly observable. So really the problem is that now we'd like to infer those actions from observations or state sequences. In order to do imitation learning when we only have observations and no actions, we're going to have to do two steps. In the first steps, we're going to learn a model of inverse dynamics. So what this means is that we're going to learn a distribution over actions given the current state S and the resulting state S prime. We're going to do this by supervised learning, where we're going to record some data that is sampled by executing random actions with our existing system. So here, this data is not coming from experts, right? So let's say we've got a robot, we've engineered it, we've manufactured it, we have it, and then we can simply get it to execute some random actions in the environment and then record what is the sequence of state, action, resulting state S prime into a data set. Based on this data set, now we can use supervised learning to learn a distribution over the actions that could have resulted in going from state S to S prime. Now in the second step, then we're going to do behavioral cloning. In other words, we're going to learn a policy to predict actions given states, but we're going to do that by combining together the expert trajectories that only consist of states with our inverse dynamics model that allows us to fill in what are some of the actions that we couldn't observe. So the idea is that we have some sequence of states that come from the expert trajectories. So let's say S and S prime. And now we use inverse dynamics model to compute a distribution over the action A that could have led the robot to go from S to S prime. And then we simply sample an action. We're going to call it A hat, just to denote the fact that it might not be exactly the action that was executed, but it's an estimate of what might be the action that led to S prime from S. So given a pair S and S prime, then we infer an action A hat from the inverse dynamics model, and now we can use that to learn by supervised learning to predict actions given states. We're now ready to define some pseudocode for doing imitation learning from observations. So we're going to start with some expert trajectories, tau e, but now the important thing is that these trajectories will only consist of sequences of states, no action. Then after that, we initialize the agent policy pi at random, and then we're going to execute a loop in which there are two steps. The first step will consist of learning an inverse dynamics model with some parameters that we're going to denote by W. So here we're going to sample a bunch of state, action, state triple by executing our policy pi. At the beginning, this policy is random, gradually it's going to improve, but the point is that we're simply generating some triple state, action, state from our current policy. Then based on this, now we learn an inverse dynamics model by supervised learning. We're essentially maximizing the probability of the action A given the current state st and the resulting state st plus 1. Once this is learned, then we can update the policy parameters theta. We're going to do this again by supervised learning, but instead we're going to consider expert trajectories. So our data for this step consists of pairs of st and st plus 1 that come from the expert trajectory. Now we need an action, so we're going to fill in the missing action with our inverse dynamics model by simply sampling an action given the current state st and the resulting state st plus 1. And again, this action is an estimated action, so we're going to denote it by a hat. Once we have st with a hat t and then st plus 1, we're ready to learn in a supervised fashion what might be a good policy that predicts an action given a state. So that's our last step here, where we take the argmax as the sum of the log of the probability of AT given ST. To conclude this module, let's compare empirically the performance of imitation learning techniques with and without observing actions. So in 2018, Torabi et al. Reported some interesting experiments on 4 robotic tasks. So you can see here little pictures of those robotic tasks, and then below each picture we've got the performance of some algorithms. The y-axis is the rescaled performance between 0 and 1, where 0 corresponds to the random policy and 1 is the performance of the expert policy. So our goal is to approach that. The x-axis corresponds to the amount of interaction with the environment, but here it's the amount of interaction after we've observed the expert trajectories. So the idea is that if we're doing imitation learning, we observe an expert, and the idea is that we should be able to learn a lot from that without interacting with the environment. So that means afterwards we should be able to reduce the amount of interaction with the environment, and so that's why it's interesting to have the x-axis that looks at that, and the idea is that we'd like to approach the expert policy without having to interact too much with the environment. Now, some algorithms do require interaction with the environment after they observe the expert trajectories, and so that's the case here for the GAIL algorithm that we discussed. So the GAIL algorithm is in blue, and then you can see the curve varies with the x-axis, which means that it does require some interactions with the environment after it has observed the expert trajectories. Now, in contrast, if we look at the BCO algorithm, which is in red, this one has a flat curve, so essentially a line, and that means that it does not interact with the environment after it has observed the expert trajectories. So this algorithm that we saw just before has a loop, but here what they tested is essentially just one iteration of the loop. So that's why it says BCO 0. So the 0 indicates that it just does one iteration of the loop, and that means that it learns from interactions with the environment, an inverse dynamics model, but before it sees the trajectories from the expert. So here the idea is that if you have a robot, for instance, when you buy it, you can use it in your lab to interact with the environment and learn as much as you want an inverse dynamics model. But then given a task after that, then you observe some trajectories from the expert, and you'd like to arrive at a policy, ideally without any further interaction with the environment. And that's what happens when you just do one iteration of the loop for the BCO algorithm. So again, that gives us a curve that is aligned, so it's flat, no interaction with the environment after it has observed the trajectories from the expert. Now, if we want to know how much interaction happened before observing the expert, so that's written right beside that line, and we can see that this amount of interaction is not very high. And that's because it just needs to learn an inverse dynamics model, which is simpler than optimizing a policy. Okay, so when we look at those results, really the main point here is to compare algorithms with and without observing actions. And what's really interesting is that the BCU algorithm does not observe any actions, and yet it performs quite well. In fact, without even requiring interactions with the environment after observing the expert. So it performs quite well in comparison to GAIL, which has access to the actions. So this is quite remarkable, and it demonstrates that even if we don't observe the action, we can obtain good results.